And then we need to make a new chapter. Stack new chapter 7. All right. This is. What's up, Brian's? How's it going? I feel like I haven't seen you in a while. How's school treating you? If I could do it. Oh, you're in summer? That's good. If I could do it all again, would I? Grad school or undergrad? Is the question, if I did it again, what would I do? Or would I do it again? I would do undergrad again. Knowing what I know now, I would do undergrad again. Grad school, it would be iffy. I'll be honest with you. Grad school was rough. We don't need this. For sure. Oh, for sure. That's true. I don't have to worry about that, but it's stressful in other ways. You know what I mean? Enter doesn't work there? That's useless. I mean, it's very stressful in other ways. Sure. Okay. So, apparently, there's another set of types that are similar to what we were looking before that are kind of like, they represent any type. So you can have like a data type like this. Any A. And I think we're going to need some stuff in here. Where you just started. What's up, Bloomy? How's it going? Yep, Existential Types, and that's chapter. We got Benjamin Franklin Scout here too. 3.2 is good. What do we need here? I think we need. Oh, that's fun. There's something. Can't slack. That's the hard part. Language. Existential. Do you think eventually people pass college? I mean, there's certain people that definitely have a harder time with college than others. Like I know for a fact that a lot of students that I had a lot of trouble with college because they went straight from like grade school to high school. Well, that's not, you kind of always do that in the US anyway. And then they went straight into college and they just had no motivation to complete college. So that was, I think that was a huge issue, the motivation problem. Self-discipline in general is hard in college, right? There's just so many distractions as well, right? Like you know, it's really easy to be distracted in college. Apparently there's another way to write this in that the Gadget syntax. I probably need yeah, that's okay. So that's good motivation right there. Like just the fact that you don't want to do that. So since I noticed a few people who are here that were here what's today? Tuesday? On Sunday? So I'm working on a new Git repo of basically it's gonna be, the idea is that it's gonna be just a quiz for me to continually work on so that these things make sense. So I put some of the harder questions that we've experienced on the stream thus far, and just like, let's go implement a bunch of instances and try and understand what's going on. So if you guys have any suggestions for stuff there, I'm gonna stick this in here, and we'll go from there. But I thought this might be an interesting idea, because I constantly get out of practice with some of these things. If you don't do them a lot, you know, you lose your abilities to do things very quickly. So I thought it would be useful to have a setup where we just, like, maybe once in a while we'll just go through and just do the do some instance definitions for some hard problems. Why do I always want to do that? I thought that might be interesting. Make a little quiz. I don't know if anybody's interested in that, but I started that. Yeah. Okay, so what's the key here? These any are the nightmares in college people who don't go to class and don't do homework? No, they don't bother me at all, because I never have to deal with them, right? Like, if you have students like that, you just ignore them because they clearly don't care. The only thing that's a little annoying with them is when they come to you at the end of the year and ask you to do makeup, or not makeup, but like extra credit. Any types can contain anything. What's the just sometimes sit in class, and then on the exams day the other half of the class shows up. Yes, there are definitely people who do that in class, but some of them are doing it for like actual good reasons. Some people are just doing it to do it. Like I took classes, or I took a few classes in college that were a waste of my time, and I didn't go to them and just took the exams, but I did fine, so that wasn't an issue. But that's not for everybody. Why is Moobot so slow at picking up viewers? I don't understand why that's so slow. Yeah, there's definitely some, like, it's the first time in your life where you're really responsible for yourself, for a lot of people anyway, not for everyone. All right, so these things can contain anything. How do they word this? It's like a, he writes something kind of funny. They have an identity problem. The type system has forgotten what they are. That's the idea. So the type system forgets what A is. Well, that's actually a good point too, Lumi. Yeah, school isn't for everyone. I have a lot of friends who did not do well in college, and not because they're dumb people. It's just that they don't work well in that system. So I don't disagree with you there. I'm a product of the system, so. All right, so this is kind of cool. You can have these types. Let's see if we find a cool use case for them. And Ryan, there's cases where professors really feel like if you don't show up, you're literally disrespecting them. So, but not all of them feel that way. So you can apparently do something like, and it just says list of any. So it's sort of forgotten these inner types. I suppose that the only problem with this is that you can't do anything with these types, right? Like, because the type system has forgotten them, they're basically useless to you. Is this big enough, by the way? Can everyone read this? I always feel like it's too small. Whenever I look at other people writing code on streams, I think their font's too small, so maybe it's just my eyes. like you could never write a function to do anything with this 5, right? Ever. I suppose. Maybe there's ways to do it, but I don't think we've learned them yet. You could do it the other way, where you had a, like our H list system. I think you could do it that way, but I'm not sure how you do it here. Although maybe we'll learn. Okay, so actually maybe that's what this whole chapter is about. Existential types can be eliminated, consumed via a continuation passing. An eliminator is a rank 2 function which takes an existential type and a continuation that can produce a value regardless of what it gets. Elimination occurs when our existential type is fed into this rank 2 function. To clarify, the eliminator for any is elim any. Elim any. Let's use the GADT syntax. GADIT, sorry. For all A to R, right? It's got to be a continuation pass. Any R. Oh, and then I gotta get rid of these primes. I don't show indicators of failing. What do you mean by that? Was that in regards to the Oh, okay. I see what you're saying. Never mind. Sorry. Oh, I need rank n types. Yeah. I mean, it's all designed to build on top of each other. So in theory, you should get, you should build up from there. By the way, I just noticed this as well. Somebody followed the stream, I think after we left. Well, actually, it was like 9 hours ago. Phil Zook. So hopefully Phil Zook shows up at some point, we can say hi to him. Them. Okay. So pay attention to where the A and R types are quantified. The caller of elim any gets to decide the result R, but A is determined by the type inside of the any. The caller of elim any gets to decide the result R, but A is determined by the type inside of the any. I mean, just continue doing what you're doing. If you got a 3.2 this semester, continue what you're doing and you'll be fine. I wouldn't worry about it too much. Well, I mean, don't not do the work, but no reason to stress yourself out. Are functions of type yeah, I mean, if you're doing that, then you're going to be fine. Just continue doing that. Don't stop because, for whatever reason. Yeah. So here's the question. Are functions of this type interesting? I'll write it here. That's not it. Interesting. For sure. In high school, I never did homework, but in college, I did. I was dumb in high school, though. I don't know what happened. Something clicked for me when I got to college. Okay, so are functions of the type for all A to R interesting? Why or why not? That's kind of a weird question, but I mean, this is the CPR stuff, right? Continuation passing. What's the R stand for? I already forgot. Oh, it's just style. CPR. Continuation passing. CPS, not R. Continuation passing style. So I find this question really strange. Does anyone else find this question really strange? Let's see if there's anything that I should be thinking of. Oh, I see. Yeah, I was thinking about this before. When I read this the first time, I did think about this. So these functions can only ever return constant values, as the polymorphism of their input doesn't allow any form of inspection, right? So we don't know what A is, so the only thing we can do is return, it looks like const almost. Yeah, more or less, Ryan. What's going on, Oren? How are you? I forgot you sent me something via Twitch chat. I immediately forgot what it was. Let me look that up. I responded to you, but I don't think I got a response back. Oh, it looks like you just did it. Yeah, so I think that I added, did I? Hang on. What is that? Topics? Yeah. I think Moobot just updated for me, by the way. I think I put Nix in here, but let me add that link there. Whoops, I just deleted it like an idiot. Hang on. Let's add this link to here. Copy, edit. Add Nix. Why is it called pills? Nix in pills. I don't understand what that means. Okay. So there's this. Put that there. Okay. Sweet. Thanks for that. Matrix pills. Oh, I get it. We're taking the blue pill. I get it. Okay. I didn't catch that the first time out. That's not what I wanted to do. I want to go here. Okay. So we added another thing. I feel like I should add a command for that quiz thing. I think that could be. I like that that definition. Is anyone find this interesting? This idea? I don't know who heard this, but this is gonna be like our little quiz. Not this. Hang on. I'm making a command real quick. So type Rodeo. Our type Rodeo quiz is at there. Save. Okay, cool. So anyway, if anyone's interested in either of those, I just made this as well. Except I spelled it wrong. I almost did it again. Okay, sweet. Let's get back to this. So these functions are interesting because they can only return constants for the same reason that for all a to a can only ever be a like an identity function. Couldn't find contravariant at first is because it was recently moved to base. I think we figured that out. I think that I don't remember. We can look, but I think that we figured that out. Let's go check. I think that was in chapter something 3, although I don't really know. Nope. Exec, grep, contra. So let's see what we did here. Yeah, so we eventually figured out contravariant and invariant. I think what you were seeing on the YouTube video was just me not realizing that I needed to compile these things. So I needed to run like stack build so it would compile the actual source of these libraries before it would do any type configuration. It would actually annotate the types in Visual Studio Code. I don't remember exactly what you were looking at, so it's hard to know for sure. But anyway, we did figure that one out eventually. Okay. So this approach of existentializing types and later eliminating them is more useful than it seems. As a next step, consider what happens when we pack a type class dictionary along with our existentialized data. What is this? A type class dictionary. Okay. I don't know what that means. Ugh, can't type. Supposedly I'm supposed to be getting my new as a dictionary. What does dictionary mean here? Anytime I see the word dictionary, I think of like Python dictionaries. Okay. So I should think of it like a record type, basically. Okay. Well, as long as you guys think it's also probably not a great choice. But so conceptually I can think of type class dictionaries as more or less record types at runtime? Sorry, type classes and instances are represented that way at runtime. Okay. So the definition of has show is remarkably similar to the Gadit definition of any, right? Because we have like a T to has show. But I suppose, oh yeah, right. This is a Gadit. Okay, that's useful. Thank you. When I read this the first time, I was like, I don't know what that means, dictionary in this context. But this is Gadit syntax. So this T is like a for all T. So yeah, basically, you know, for any type T, we can represent it as has show to give it a show instance or something. This constraint requires a show instance whenever constructing a has show, and Haskell will remember this because a show instance was required to build a has show. Whatever type is inside of has show must have a show instance. Remarkably, Haskell is smart enough to realize this and allow us to call show on whatever type exists inside. We can use this fact to write a show instance for has show. Okay. By the way, these aren't like problems, it's just code in the book for now. So instance show has show where show has show s equals has show. Oop, I need a space here. Show s. Okay. Neat. I think we get to the point where you can write like a has function where you can just feed it show, and then we just have a more generic version of this. Okay. what happens to this instance if you remove the show t constraint from has show? My assumption is this will fail because show s doesn't have a show instance. This will fail right here. That's my guess. We're gonna get squiggly lines under here if we remove this show t. Haha! I like when I can actually think of stuff, you know? Like sometimes writing these instances is really hard, but this one made perfect sense to me. I like when it does. Anyway, I think that seems logical because we're trying to show something that the type system has no idea what it is. It's just some t. So it needs to know that it has a show instance, otherwise you can't call show for it. All right, neat. More generally, we are able to write an eliminator for has show, which knows we have a show dictionary in scope. Yeah, see, this is where that term dictionary really threw me off, but I feel more confident about it now. For all a show a to r. I suppose okay. So the multi-line version of this is to do it this way. It seems to not like this, but we'll try it. It would be nice if this like actually type checked, or not type checked, excuse me, but gave us the syntax highlighting that we're expecting. But that's okay. Usually this is green, right? But it doesn't think that it's a type declaration for this function for whatever reason. Okay, write the show instance for has show in terms of elim has show. Okay. So we're basically going to comment this out, and we're going to write instance show as show where yeah, I guess this is the only way this works, right? Because this show is your a to r function, right? A to string function. And then you must return r, which is a string, and you need to give it the has show, which is just HSS. This is has show s, but I guess it's really t. Just keep strumming. The only thing holding me back is time. The only thing holding back anyone is time, I suppose. I don't have enough time to do all the things I want either, so I don't think anyone does. Alrighty, so from here, the next thing we can do is apparently just have straight up Python in our Haskell. So we're going to talk about dynamic types now. So this pattern of packing a dictionary alongside an existential type becomes more interesting with other type classes. Typable class provides type information at runtime and allows for dynamic casting via cast. Let me show that. Oh, this is the wrong chapter. 7. Import data typable. Is it GHC typable? No. Type cast. Right, so given an A, we can try and convert it into a maybe B, apparently. We can existentialize typable types in order to turn Haskell into a dynamically typed language. Using this approach, we can write Python-style functions that play fast and loose with their types. As an illustration, the plus operator in Python plays double duty by concatenating strings and adding numbers. We can implement the same function in Haskell with dynamic. Isn't that cool? So we're gonna implement the Python plus operator in Haskell just for the hell of it. So we have a get it. It's still, every time I say that, I still feel like it's wrong, by the way. Probably only because I've never heard anyone else say that term before. T dynamic. I think I just need to hear somebody say get it as well. So then we can write an elimination function for this. Oh, these should be 2. They're not supposed to be 4, but oh well. Ah! Did I mention I'm supposed to be getting my keyboard soon? Pretty excited about that. But it's taking forever to ship. It's been on back order for like a month and a half. F dynamic A. Where's that coming from? FA. Okay. We can implement from dynamic, which attempts to cast dynamic to an A. From dynamic. Typable A. Dynamic. Maybe, oops. So that's our R in this case. Right? So we're just feeding that cast function from here to generate our R, which in this case is a maybe A, using that elim dynamic function. And then apparently we need a helper function, which is a little bit of a monster. So bear with me while I write this one. Wait a second. So if I oh, that's not gonna work. What just happened? The bot is not in your chat yet. What does that even mean? I'm not dropping frames or anything weird, right? I dropped a few frames there, but not a lot, so Moobot seems to be being annoyed today. Okay, so lift D to, oh, I know what I wanted to do. It's not fixing the typing or the space. It assumes that if I'm using 4, I continue using 4, I guess. Oh well. Bear with me while I write this one. This one is a little long. Typable B. R. Dynamic. So that's our first dynamic. Dynamic. That's our second dynamic, the B. Just keep trying what? Sorry, I overthinking school? I 100% think you're overthinking school. I think you just need to keep at it. Yeah, for sure. Don't stop doing that. Don't stop doing that. Unless you can find like the best internship in the world or apprenticeship that doesn't require school, that's only going to help you. Yeah. Or Wozniak, or those other people that figured out all this stuff in their attics and closets, or sorry, garages, not closets. So dynamic dot f at a d1. Okay. Type applications. I don't think that was mentioned, but that's fine. We can usually figure those out because the compiler tells us. What is this one from? This one is type something. It might say in the next. Oh, I'm just not done yet. Yeah, I added that. I'm just not done yet. I think I need to finish the. I might also need to reload the yeah. Let's try restarting GHC. Type applications. For all ABR. Dot. ABR. Dynamic, ABR, maybe dynamic. D1, D2, F. Yeah. No, that's fine. I'm a little confused at why this isn't working either. I thought we just needed type applications. Maybe like if we just run stack build, there would be more information. Oh, that could be. Usually it tells us things like that. Let's try that. Right, because that A is a different A, right, than this one without scope type variables. Good call. Thank you for that. I'm still not used to all this stuff. Okay, so what do we got going on here? Because this is kind of a monster. Alright, so we're gonna take an AB to dynamic. So F is of type ABR, and we F map dynamic. Oh my goodness. This is a bit of a monster. I feel like my H format's not working anymore, because it used to format this kind of code. So maybe it's broken. Anyway, that's kind of a beast of a function. Maybe we'll come back to that after we finish what we're doing. So using this, we can apparently write The Python plus function. What's the error from Python? We'll use the same one. More as a joke. Right. Dynamic 1, dynamic 2, and then an operation. A binary operation. That'll be plus. And then... Oh, well, you know what's kind of funny in here is that he shows the cases where you add strings and ints together with show, like you just convert everything into a string, except like that doesn't even work in Python. You're not even allowed to do that. So, but anyway, we'll show them because it's kind of interesting, I suppose. Okay, so these ones need to take a binary operator, so you're gonna have basically string A, int B. Oh, yep, I need a $sign as well. So string A plus plus show int B, I guess. And then int A string B show int A string B. This comes from data something. I think it comes from here. Hang on, I gotta sneeze. Where's list A? Just string. Which I'm sorry, Norf. I still don't know how to say your name. I'm gonna call you a funny one. Wait, no, we decided this. I decided I was gonna call you Murph, right? Which list A? We have not used list A, so I'm a little confused. This A? Why is this failing? Oh, I'm missing I don't know what this is though. What's a sum? Google, help me. From foldable maybe? We'll try that. Okay. Uh, oh, in Python. I see what you're saying. Um, yes, that is list concatenation in Python, I'm pretty sure. Um, oops. Yeah, it's just list concatenation in Python. Oh, I'm sorry. I see what you're saying now. If we wanted to define uh, list concatenation, how do we do that? Well, I guess we are doing that, right, by doing this. Because this A is really a list of car, right? So we're really doing list concatenation just with strings, obviously. So I suppose you could have list. Maybe you can have listant with plus plus in the middle. I don't really. We could try it. Let's see if I can do that. I think I would just write like this. Yes, so you can do that. Seemingly. I don't know what this asum function does. Oh, I see. It will only return a result for the case that matches, right? So you can only match one of these cases is the idea. So if you use asum, you're just going to have like a fold over a bunch of nothings and one value, or you're just going to have a fold over nothings, right? So you'll get nothing back. Yeah. Yep. Wait. Interesting. It actually uses. Here, let's go look at the implementation. It uses alternative, which is interesting. What is it using alternative for? Oh, it's just returning the first thing that matches, I guess. Just started raining like crazy outside. So it only returns the first thing, or I guess nothing. What's empty? I'm guessing empty is like nothing. Comes from alternative. Yeah. Empty in this case is just nothing, right? FA. So this is the maybe applicative, and yeah. Yep. No, I think it makes sense. I've just not seen this function before. Okay. I suppose you can just use a regular old fold though, right? Oh, you need the alternative for the types to work out. I guess. No, no, no. That doesn't make sense. Doesn't make sense. I don't know. Kind of an interesting function. Anyway, let's try this thing because I'm curious. Uh, that's the wrong REPL. You know what? I do want to look at that now. Nice. Oh, it's not in here. Oh, of course it was. A sum here. There it is. So nothing in R is R, L and anything is L, right? Because this would be a maybe something. And then it'll just use the from maybe as expected. Sure. Okay. Nice. That's actually really useful. Oops. Okay, so this does what we think it does. And this will return nothing if none of these matches, or it will return maybe something for the first one that it matches, and then we'll just from maybe it into an error if we have to. Well, this technically isn't correct. We don't know that it's int and string necessarily, so we'll just write for plus. And let's go try and use this. Apparently we need to set a default, which I've never done before. Oh, first we need to set type applications, and then we need to write default int. Okay. And we need to write some kind of ugly code here. From dynamic at int pi plus dynamic 1 to, well, it doesn't quite look like Python, but this is dynamic typing, I guess. The thing that's a little weird about it is you need to write this at. Can you not just write this? Oh, we don't have a, okay. So it looks a little funny saying that this is like, you know, as dynamic as Python, because you need to write like from dynamic at string, but you know, you can do weird stuff like that, I guess. So that's kind of interesting. Okay, so it says if you were particularly plucky. Plucky. Has anyone ever heard the word plucky before? Plucky. Having or showing determined courage in the face of difficulties. Okay, I've never heard that term before. With this approach, you could embed a fully functioning, dynamically typed language inside of Haskell. The boilerplate around writing type-dependent pattern matches would amortize down to O to the 1, apparently, as more of the standard library were implemented. But, just so we're on the same page, just because you can doesn't mean you should. Makes sense. However, there's an interesting philosophical takeaway here. Dynamically typed languages are merely strongly typed languages with a single type. That's pretty cool to think about. I'll say it again. Dynamically typed languages are merely strongly typed languages with a single type. Okay, cool. All right, so if we notice before, this thing here and this are basically functionally identical, right? You basically just have a name and some constraint, and a type that returns the type constructor. Data constructor? Type constructor. I said it right the first time. So clearly there must be some sort of nice thing that you can do to abstract over the pattern, and there is. So we need another one of these language extensions, because what would Haskell be without language extensions? It would still be a good language, but there's a lot of useful extensions. Okay, so we need this thing called constraint kinds. Then we can write the following. Pretty useful. Uh-oh. Okay, we also need kind signatures. And could you imagine if we had to remember all these? Well, we needed to remember scoped type variables, I suppose, but this is a lot to remember. I already forgot what it was. Kind signatures. Oh, we need data kinds as well, apparently. Okay, now it seems to be fine. Okay, so, oh, well, and these come from GHC typelets, I think. Let's see if we got it. Nope, they're not from GHC typelets. Where are these from? I thought they were from here. Oh, let's Google it. Data kind. Thank you. Yep. Okay. So from here, we can apparently write an eliminator for has. So this is going to look very similar to the other ones. For all A to R, has. Oh, sorry, I need some other stuff here. CA. Nope. For all C dot CA A to R has C R F has A equals FA. Allow ambiguous types. Okay. So okay. What's the problem with this one? Well, that's not good. Oh, this is supposed to be an A. Yes. My bad. That's funny. This happens all the time. I love it. You guys are freaking on top of this. I only happen to catch it just because I'm looking at the book, but you guys just catch it. It's awesome. Okay, so apparently we can write things like this now. I'm using the tick here because we've already defined these things inside here. I guess this also has to be a tick, huh? No, that's not right. What's wrong here? Ugh. Not dynamic, has typable. Excuse me. I don't drink enough water on stream. I need to drink more water. I get in the zone and then I just keep going. Okay. So sometimes we want to be able to talk about multiple constraints at once, like the function which determines if its argument is mempty. So let's look at this example. Is mempty monoid a eq a to bool is mempty. Well, we can just write this in point free notation. Right, so if we write this function, we have multiple constraints, but apparently we maybe we'd like to construct a has around this constraint, right? Because we have two constraints now. Unfortunately, there is no type level lambda syntax, so we're unable to turn this type into something that's curryable. So GHC won't allow us to construct a has for this. The problem is that type synonyms must always be fully saturated. We're unable to talk about being monoid and eq in its unsaturated form. Only monoid and eq a is acceptable to the compiler. Fortunately, there's a solution for constraint synonyms, though not for type synonyms in general. We can instead define a new class with a superclass constraint and an instance that comes for free, and an instance that comes for free given those same constraints. Sorry, there's extra text in there. I had to make sure the sentence was correct. This is known as a class constraint. Goodness, I can't speak. Constraint synonym. Okay, so you can write the following. Okay, so this thing is called constraint synonym. Known there's write a line of code, add a language extension. Write a line of code, add a language extension. Eh. Okay, now this whole thing is Brett. Undecidable instances. Okay, we've gotten to the point where it's write a line of code, add 2 language extensions. Okay, so that works then, but you apparently need some. I should probably write that under here for future reference. So this was that one, and allow ambiguous types, right? Yes. Well, technically it was like this. I should probably start writing those just generally so that we have them. Okay, so you can use these things. Let's try it. So foo equals has true has monoid eq. Elim has is mempty foo. Because mempty is false, right? So if we write, or is it supposed to be list? I think this is supposed to be empty list. Yes. Okay. So I just wasn't sure what we were doing here, but this is a list. So mempty for a list is the empty list. So it doesn't matter what you put in here. It will always be false unless you give it an empty list. Interesting. Okay. Scoping information with existentials. This is kind of funny to me. The first thing it says for this is necessary extensions, rank and type. But I don't think it said that for this chapter. It did not. It's kind of funny to me. Okay. Should we do this in another? We probably don't need to. So we're going to talk a little bit about scoping information with these. And we need some imports. Data, IORef, data, oh no, system, IO, unsafe, perform IO. Okay. Existential types can be used to prevent information from leaking outside of a desired scope. For example, it means we can ensure that allocated resources can't escape a pre-specified region. We can use the type system to prove that an HTTP session token is quarantined within its request context, or that a file handle doesn't persist after it's been closed. Interesting. What time is it? Okay, we got some time. Hopefully we can finish this chapter. I thought we were going to finish like 3 chapters, but it always takes me longer than I thought. Because existential types are unable to exist outside of their quantifier, we can use it as a scoping mechanism. By tagging sensitive data with an existential type, the type system will refuse any attempts to move this data outside of its scope. Haskell's ST monad is the most famous example of this approach, lending its name to the approach, the ST trick. Anyone know what ST stands for? Maybe somebody knows. Scoped type? I don't know. If you're unfamiliar with it, ST allows us to write stateful code, including mutable variables, to perform computations, so long as the statefulness never leaves never leaves the monad. In other words, st allows you to compute pure function using impure means. That's cool. The amazing thing is that st is not some magical compiler primitive, it's just library code, and we can implement it ourselves, assuming we're comfortable using a little unsafe perform IO. Of course, this is not a comfortable situation. Unsafe perform IO is fundamentally unsafe, but observe that there is nothing inherently unsafe about mutable variables. Not the presence of mutable variables that makes code hard to reason about. So long as all of its mutations are kept local, we know that a computation is pure. Mutable variables on their own do not cause us to lose referential transparency. Referential transparency is lost when code relies on external mutable... I'm almost done, by the way, sorry. Referential transparency is lost when code relies on external mutable variables. Doing so creates an invisible data dependency between our code and the state of its external variables. It is these cases, and these cases alone, that we need to worry about. As such, it's completely safe to have mutable variables so long as you can prove they never escape. The ST trick exists to prevent such things from happening. Enough jibber jabber. Let's implement it. Okay. Stateful thread. State thread. Okay. Useful. Very useful. Thank you. So yeah, it's apparently just used to do mutable things, but inside of one scope, such that you don't lose referential transparency. That's how I'm reading this. Thank you for looking that up, though. I probably should just go look it up at some point. Or I mean, we don't have to now, but every time. I'm just gonna say every time when that happens because it's literally every time. I hate this. Why do we have four tabs all of a sudden? It's driving me a little nuts. How do we fix this? Give me 2 seconds. Let's see if we can find it real quick. Settings, tab. All right, so we can probably fix this with a :%s /space/space/space/G. Oh, that's all right. There we go. Okay, so hopefully we can get back to... Seems to still want to make... See that? Indent using spaces. That's fine. Weird. Well, it's fixed now, seemingly. I didn't realize this was down here. But apparently it defaults to 4. So, what did that say? Let's see if we can find that. Detect indentation from content. Settings. Indentation. I mean, it's 2 here. Controls whether... Oh, maybe this is like a new thing. What if we turn this off? We'll try that. Sorry, I was getting very annoyed by that. Okay, so what's 1? Hang on. notice here, this S is a phantom type parameter. The variable exists only as a place to put our existential type tag. We'll better see how this is used in a minute. Applicative and monad instances can be provided for ST. To ensure that our unsafe IO is performed while it's actually still safe, these instances must be explicitly strict. This is not necessary in general to perform the ST trick. It's only because we will be using unsafe perform IO for this example. So in practice, you don't need to do strictness here, but we're going to use it because apparently it's easiest to like think about. Okay, I have to remember how this works. So why do we need, I forget exactly how seek works. That's kind of where we've done some code with seek, but it's been a little while. It looks like const. Where'd it go? So it's like, okay, that's right. It's like, it's a sequencing a strict sequencing operator. So it does this thing, i.e. Evaluate A. Why do we need a composition though? I don't know why we need a composition. I thought it would be equivalent to writing this. Oh, it is equivalent to writing that because of the $sign. Right, we're just pre-composing these functions and then applying it to FA. This is completely the same. You could also write this. Totally fine. Okay. Anyway, I feel I was a little confused about that for a second there. I prefer this over the dot from my, it'll be easier for me to think about later. Anyway, going off on a tangent there. Applicative STS. Partially applied pure STF. By the way, these are given to me. I'm not writing these on the fly. STA equals seek F seek A. Here we would need another $sign, and that would be fine. Okay. Monad STS. So this is an incomplete monad definition, which is kind of funny. Although maybe you didn't need to actually define, you don't actually need to define return, and I'm wrong. I thought you'd need to define return. Seek A FA. Oh, I thought that you had to define return. Maybe that's recently changed. Or maybe I'm just wrong, like completely wrong. Maybe I feel that way because we always used to write, you had, okay. Is it specifically 7? Like, because it might be that in HPFFP that we had to write it and now we don't have to write it in GHC8, something like that. That could be. All right. So where I'm a little confused. I don't see any unsafe perform IO going on here. These seem to be pure, but maybe it's going to come down to like how we use them. Let's see. So now we have a new type st ref sa equals nope, wrong button. Seriously? What? Why would you do that? It's not what I'm asking you to do. Weird. Okay, so now we have an stref. I feel like I'm missing something. What's unsafe here? Oh, I see. We're gonna combine st and stref. I see what's going on here. I was a little confused there for a second. So we're gonna use strefs and sts with these unsafe operations. So anyway, I'll keep reading. Pay attention to the fact that stref also has a phantom parameter, right? S. This is not accidental. S acts as a label, irrevocably nodding a stref with an st context that created it. So that way, these things are forever linked because the s's need to match. Function wrappers for stref around ioref are provided, each of which unsafely performs IO. For example, we'd like to be able to create new strefs. Oh, I'm missing. Okay. So pure takes our A and makes. Oh, yeah. It takes an stref and turns it into an st. This is our. I should probably start from here. We're going to make an IO ref A and then perform that to give us an IO ref A. Wrap that in the stref and then wrap that in an st. We're working left, not to the right. Okay. Has anybody used these before, like in actual production code? Just out of curiosity. pure unsafe perform IO write IO ref Sorry, there's a lot of code on this page, and I keep reading from the wrong place. This is read IO ref. There you go. Okay. To be fair, I still don't know how to use these yet. We're gonna find out. Modify. Also, I'm why does this keep... Moobot's being a little slow right now. Modify stref, except that's not the next one. How many more pages do we have? I really need to... I'm gonna probably get off a little bit. There's only a few more pages, we'll be fine. I'd like to get off at least at 9:30. I decided yesterday to run a 10K just out of the blue, and my legs really hurt. So like sitting here for this long is kind of getting very uncomfortable very quickly. So, but we'll try and finish this chapter. So, write stref sa a to a sorry, apparently I'm just generally tired, mostly for performance. Yeah, okay, so people are just using it when they need to do IO, but they still want the purity. Okay, so given a ref, we're going to write pure unsafe perform IO write IO ref unst ref. Okay, so this gets us an IO ref, which we write. We make sure that we write it, and then we wrap it back up in a ST. Neat. Modify ST ref. ST ref. So that's our modification function. Do a read stref ref write stref ref fa. Okay, so we read from it, we modify it, and write it back. Okay. And finally, we provide a function to escape from the st monad. This is merely unsafe run st, but with a specialized type signature. Run st. Oops. Okay. At 1, we see the introduction of the st trick. The type for all STSA indicates that run st is capable of running only when running only those STs which do not depend on their S parameter. We will discuss why exactly this works shortly, but let's first convince ourselves that runst lives up to its promises. We can write a safe usage of st, one which uses its state to compute a pure value. Okay. So safe example sts string do okay. Yeah, I think there's definitely some like practicality of these things that I don't fully know yet. But what I'm thinking is that it's going to be useful to just get a lot of exposure, and then like when I see this stuff later, I won't be surprised by it. Like I can say, "Oh, we've seen that before," and then go read about it again or something, and then that should help solidify my knowledge. Something like that. What are these called again? Sections? Oh, well, I'm not done yet. I want to make sure I'm using the right terminology. You basically need it whenever you actually need to deal with mutable state. Okay. We have mutable state with arrays. Like the internal implementation. Okay. Interesting. Okay. This is cool. Okay, so now that I see this type error, this makes a lot more sense. So like I can only so what so this is basically what we're gonna do. Like you're gonna have an sts something that does some mutation like this, and then you're just gonna read it back out, and then like do other things somewhere else. But this is what essentially what we're. Are we going to input an stref in most of these functions? I guess that's my question. So like we're are our useful functions going to take an stref, do io, and then read it back out, or are they going to be like this, where the reference itself, the io ref itself, is made inside the function every time? I don't know what the right question is. Yeah, okay. Pure thing coming in, pure thing coming out. What happens in the middle? We don't know what's going to happen. Okay, so this is kind of like a weird example, right? Because we don't take in an stref, but it gives you an idea of what this looks like. Okay. So indeed, runst seems to work as expected, but how? Let's look again at the type of run st. So let's look at the type of run st here. So for all s st sa. The word for all here acts as a quantifier over s. The type variable exists in scope only within stsa. Because it's existential without a quantifier, we have no way of talking about the type. It basically doesn't exist outside of its for all. And this is the secret to why the st trick works. We exploit this fact that existentials can't leave their quantifier in order to scope our data. The quarantine zone is defined with an existential quantifier. We tag our quarantine data with the resulting existential type, and the type system does the rest. To really drive this home, let's look at a specific example. Take again the case of run st new stref true. We specialize the type of run st here. It results in the following. Okay, so let me write this here. So we're gonna specialize run st so for all s st s st ref s bool. Right, so that's basically what we're doing. Okay, written like this, it's more clear what's going wrong. Type variable s is introduced and scoped at 1, but later references s, this s. Yeah, okay. So at this s, we've referenced s, and you can't do that. At that point, the type no longer exists. There isn't any type s in scope. GHC calls s a rigid scalum. Is that how you pronounce it? Scalum? Type variable. Rigid variables are those that are constrained by a type signature written by a programmer. In other words, they are not allowed to be type inferred. The human has already given them their type. A scalum is, for all intents and purposes, any existential type. The purpose of the phantom s variable in st and stref is exactly to introduce a rigid scalum. If it weren't rigid, it would be free to vary, and Haskell would correctly infer that it is unused. If it weren't a scalum, we would be able to restrict its existence. This st trick can be used whenever you want to restrict the existence of some pieces of data. I've seen it used to tag variables owned by external FFI and used to implement monadic regions which have more or fewer effect capabilities. Interesting. Okay. So that's actually it for chapter 7.